Hey everybody, Chris McClure here. We're going to now move into section R.3, and we are going to take a look at some essentials of geometry, just a review of stuff that you've undoubtedly seen before. So the first one is a review of the Pythagorean theorem. It has a long history, and Pythagoras certainly was not the first person to know this relationship between the sides of a right triangle, but he was the first one to actually publish his results through Euclid. Euclid is the one who ascribed it to him. So here's what the Pythagorean theorem says, is that suppose that you've got a right triangle, as in a triangle with a 90-degree angle. Well, it turns out that if you take the square of the length of one leg plus the square of the length of the other leg, the sum of those squares of lengths is always going to be the square of the length of the hypotenuse. Now, let's back up just a moment. What we mean by a leg of a right triangle is one of the shorter sides. These two are legs right here, A and B. The hypotenuse is the longest side. Always lies opposite the 90-degree angle. So one leg squared plus the other leg squared is equal to the hypotenuse squared. In other words, here's that famous equation right here. A squared plus B squared equals C squared. So if you know the length of any two sides of a right triangle, you could always find the third one just by using this equation. So for example, suppose that we have a right triangle where one leg is of length 4 and the other leg is of length 3. What is the length of the hypotenuse? Then all we need to do is just use this equation. 3 squared plus 4 squared is equal to C squared, where C is the length of the hypotenuse. 4 squared is 16, 3 squared is 9, 16 plus 9 is 25. And if C squared is equal to 25, that means that C must be equal to 5. It doesn't make sense for C to be negative 5, because lengths of anything doesn't make sense for them to be negative. So the hypotenuse of this triangle would be 5. Now the converse of the Pythagorean theorem also holds, that says, if that relationship holds between the three sides of a right triangle, then if that relationship holds amongst the three sides of a triangle, then automatically that triangle is a right triangle. So suppose that we have a triangle with sides of length 5, 12, and 13. Is this a right triangle? All you need to do is say 5 squared plus 12 squared, is that really equal to 13 squared? And the answer is yes, because 5 squared is 25, 12 squared is 144, 25 plus 144 is equal to 169, which is what 13 squared is. So right away, we are able to verify that a triangle with sides of length 5, 12, and 13 is going to be a right triangle. And that longest side, 13, of length 13, is the hypotenuse, opposite the 90-degree angle. Now here's an interesting application of the Pythagorean theorem. Suppose that you are standing at the observation deck, on the observation deck of a tall skyscraper. Now you could see a long way out, but you certainly can't see forever. So how far out on the horizon can you see? So here's kind of a picture here where we've got this tall skyscraper in Taipei, Taiwan. and the observation deck is 1,437 feet above ground level. Now, how far off in the distance can you observe? Well, how you could solve this is by looking at this right triangle here, using the fact that our planet Earth has a radius of 3,960 miles. So put this vertex right here of the triangle at the center of our Earth, and we have one leg of the right triangle going up to that point on the horizon where you cannot see beyond. And then take a right angle and you're up at where you are on the observation deck of the right triangle. And then what is the length of this right here? Well, it's the hypotenuse of this right triangle. Now, the length of this hypotenuse here is going to be the 3,960 miles plus the 1,437 feet. Okay, so here's what we can do to solve for this distance from the observation deck out to that point on the horizon beyond which you cannot see anything. So let's take a look at this application of the Pythagorean theorem that says for this right triangle that d squared plus 3,960 miles squared must be equal to this hypotenuse, which is 3,960 plus, and you have to convert this, distance above ground level that you are into a mile. Now, just for convenience sake, we could use 1450 just as a nice round number, but nothing wrong with you using 1437 as well. Divide it by 5280. So this will give you a fraction of a mile. So how many miles you are above ground? Well, it's just a fraction. Well, now you can plug this whole thing in your calculator, take 3960 plus 1450 over 5280 squared minus 3960 squared is approximately equal to 2,175.08. Check this on your calculator. And then take the square root of that to get D. So D is about 46.64 miles. So you should not be able to see beyond about 47 miles on the horizon. But hey, if there's a ship or something out at sea about 46 miles away, you should be able to see it with a pair of binoculars or a telescope. All right, so there's a nice application of the Pythagorean theorem used when we're talking about right triangles. It appears everywhere. Now, we're going to quickly go through a laundry list of geometry formulas. When I give you your test, if I am going to test you knowing where you have to do a word problem involving something beyond a simple rectangle or a circle, I'll provide you some formulas. So don't worry about memorizing all of these. But here is a rectangle, and I certainly hope that you know that the area of a rectangle is length times width, and that the perimeter is going to be the distance around the outside, so it's going to be twice the length plus twice the width. All right, you just go through and add up the lengths of the outside pieces. So length plus width plus length plus width. Here's a triangle. It could be any triangle. So you can identify one side of the triangle as the base. It doesn't really matter what side it is. And then you have to measure the height. And the height is basically the vertical distance from the peak, the apex, straight down to the base, where this dashed line here makes a 90-degree angle with the base. So whatever the length of this height is times the base, and 1/2 of that will give you the area. This should make sense because, you know, this triangle is half a rectangle, and if this were a rectangle, the area would be base times height. But you take half of it for the triangle. All right, moving along here. Here's our circle. Circle is the collection of all points on the plane that are within a certain radius of the center point. Now, radius is the distance between the center of the circle out to the edge. The diameter, d, is the distance of a line segment connecting, the perimeter, but also goes through the origin. Now, when we say perimeter, what we actually mean is the circumference. Circumference is really the distance around. Circumference is going to be 2 times pi times the radius. Well, that should make sense because we know that pi is always going to be the ratio of the circumference to the diameter. For any circle, no matter how small or how large, that's what pi is. So if pi is equal to the circumference divided by the diameter, that means that the circumference is equal to pi times the diameter. But the diameter is 2 times the radius. So if you know the radius, multiply by 2 pi and you get the circumference. Or if you know the circumference, then you could divide by 2 pi to get the radius. Over here we've got the area is equal to pi times the radius squared. Here's our rectangular box, where each side of the box is a rectangle. The volume of this box is length times width times height. No surprise there. And if you were to add up the surface areas for each of the sides, well, you're just adding up the areas of the 6 rectangles, making up the sides of the box. So, like this front piece right here, that has area length times height. And this side piece here is height times width, and so forth. So here's your 6 sides of the box, areas thereof, together making up the surface area of the box. Closed box is what we're assuming. Here's a sphere, the 3-dimensional cousin of the circle. It's the collection of points in 3-dimensional space that are within r units of the center point. The volume of a sphere is 4/3 times pi times the radius cubed. And the surface area is 4 times pi times the radius squared. Here's a right circular cylinder with a height of h units, and the top and bottom are circular discs of radius r. So the volume of this right circular cylinder will be pi times the radius squared times height. Surface area will be the lateral surface area together with the area of the disc on the top and the bottom. Now, the lateral surface area, the side, think about this as a rectangle. If you can slit it right down the side and lay it out, it would be a rectangle with a height of h and a width of 2 pi r, which is the circumference of a circle. So 2 pi rh is the area of the lateral surface. And then pi r squared is the area of the top and also the bottom. So you double to get both top and bottom. So 2 pi r squared plus 2 pi rh will be the overall surface area of the cylinder. So I've got a question for you. Suppose that we've got a Christmas tree ornament in the shape of a semicircle on the top of a triangle. It looks like this, kind of like an ice cream cone. Semicircle on top of a triangle. How many square centimeters of copper is required to make the ornament? So I guess the whole thing is going to be copper. So what is the overall area of the shape? So we're being told that the height of the triangle is 6 centimeters. From here down to there is 6 centimeters. And the base is 4 centimeters. So the base of the semicircle is 4 centimeters. Interesting. Well, you know what? We just need to find the area of the triangle together with the area of the semicircle. Sometimes that's what we have to do, is find the individual areas, the areas of the individual pieces, and then add them up in order to get the overall area. Now, the area of the triangle is what we're going to try to find first. Of course, we know the area of a triangle is 1/2 times the base times the height. The base is going to be 4. The height is going to be 6. So 1/2 times 4 times 6 is the area of the triangle. Now for the semicircle, well, that's half a circle. We know that the area of a circle is pi times the radius squared. The radius is going to be 2, half of the 4 diameter. So here's pi times 2 squared. Take half of that for the semicircle. And then just simplify those numbers. 1/2 times 4 times 6 is 12. 1/2 of 2 squared, well, 2 squared is 4. Half of that is 2. So you have 2 pi here. So 12 plus 2 pi. And then you plug that into your calculator. And you get something approximately 18.28 square centimeters. Make sure that you write your units correctly. So this is the amount of copper that's required, minimum. Now, let's talk about triangles. We use triangles a lot in mathematics. Now, when we have two triangles, it could be that they have nothing to do with each other. They are nowhere alike. Or they could be similar to each other, or they can be congruent with each other. Now, congruent essentially means that they really are the same triangle, meaning that the interior angles are the same. And remember that the interior angles always add up to 180 degrees for any triangle. So I've got two triangles, the interior angles are the same, and the lengths of the sides are the same. Then that means that they are congruent triangles. So how can you tell? Well, if you don't know all of the information, but suppose that you know that for two triangles that, you have two angles and the side between those two angles, and that they're the same for the two triangles, then automatically those two triangles are congruent. Because look, if you know these two angles and the side between them, then using some techniques from trigonometry, which you'll probably take next semester, you can find these other two sides and guarantee that these two sides will be the same as these two sides for the other triangle. And oh, by the way, if you know that these two angles are 80 and 40 for a total of 120, 180 minus 120 is 60, then this angle is 60, and therefore this would also be 60. Now, if you know two triangles have all three sides being equal to each other, then automatically the angles are going to be equal. And they're also going to be congruent. The two triangles be congruent if you have side angle side that is the same for both triangles. So yeah, if you have two sides and the angle between them the same for the two triangles, then those two triangles are congruent. Now let's talk about similar triangles. Similar triangles have the same angles, but not necessarily the same side lengths. But the thing about similar triangles is that ratios of sides are the same. They are proportional to each other. So the sides are. So for example, you look at these two triangles here. They are going to be similar because they have the same interior angles, but not necessarily the same size. And remember, when you know two angles, you can always find the third angle by taking 180 degrees minus those two angles. Now, if it turns out that these two triangles, you don't know the angles, but the proportions are the same, that's fine. So let's take a look an example here. Take a look at these two triangles here. Well, you could take a look at this larger side for the small triangle in relation to this larger side for the large triangle. Now 10 is to 30 as maybe 5 is to 15 for these corresponding smaller sides, as is the ratio of this third side is to this other third side. So 10 is to 30 as 5 is to 15 as 6 is to 18. All have that same ratio of 1/3. Another way you could do this is to say that 10 is to 5 as 30 is to 15. Or 5 is to 6 as 15 is to 18. Or 30 is to 18 as 10 is to 6. Those ratios are the same for those two triangles. Here's another way that you could tell that two triangles are similar, is if you have, side angle side angle side for the two triangles, and the angle's the same, and the ratio of the two sides to each other are the same as well. You could take a look at 4 is to 12 as 6 is to 18. Are those two proportions the same? Actually, a proportion is an equation involving ratio, so I should really be more specific. Is the ratio of the side lengths the same? Is 4 to 12 the same as 6 is to 18? Or I could ask, is 4 is to 6 the same as 12 is to 18? Are those ratios the same? And if the answer is yes, then your two triangles are similar. So for example, suppose that we've got this triangle here and this triangle here as well. Now we're being told in advance that these two triangles are similar, which means that angle C is 30 degrees, the same as this one here, that angle A is 90 degrees, and angle B is 60 degrees. Also, this side is 3, this side is 5. Now, we know that the ratios of sides are the same for right triangle, or for similar triangles. This also happens to be a right triangle, but anyway. So we could say that 3 is to 5 as 6 is to x. That's one possible proportion that we could write. There's many others, but this is one that we could use. Or we could say that x is to 6 as 5 is to 3. We could also say that x is to 5 as 6 is to 3. That's another proportion that we could write. So whatever, just write a proportion that allows you to solve for x. And then once you write this proportion here, then you could solve for x. And it turns out that x is equal to 10. So this right here, this missing length right here is 10, which should make sense because over here for this triangle, this side is half the length of this side. So x would have to be 10 in order for this side from A to B to be half of its length. Okay. Now we're going to finish up just by having you take a look at this. I'm just going to verbalize this. If you're wondering why the Pythagorean is true, there's only about a couple of hundred different proofs out there proving that a squared plus b squared is equal to c squared. But take a look at this square within a square here. You got the square, the blue square, and then in the interior of the blue square, you've got this red square at an angle. Because of the fact that the red figure is a square, that you see where the vertices, the corners of the red square are hitting the sides of the blue square at essentially the same point on each side, so that each side of the blue square is divided into two equal lengths. Well, not equal lengths, but the same ratios of lengths. So this side here, or this length right here, this line segment right here, is the same as this one here, is the same as this one in here. So length of A and B. And you can see that you have, 4 blue right triangles that are congruent. And you know that the area of each of those right triangles, 1/2 times the height, which is A, times the base, which is B. So the combined area of the blue is 4 times 1/2 times A times B. 4 times 1/2 is 2, so 2AB. You follow me? So the combined blue area is 2AB. Together with the area of the red squared, C squared, you know that the entire area is C squared plus 2AB. But the area of the blue square is going to be, well, the length of each side is A plus B. So if you were to take A plus B squared and set that equal to the C squared plus 2AB, and do a little bit of algebraic manipulation and rearrangement, you would arrive at A squared plus B squared equals C squared. So this is one of many proofs out there to establish the Pythagorean theorem. So with that, we are done with this section. Now next week we're going to finish up chapter R. Now you have undoubtedly noticed that I have posted a total of 3 100 problem sections for chapter R. There shouldn't be any problems that take more than a couple minutes. So I wouldn't expect anyone to spend more than about 2 hours, 3 hours tops on any one of those problem sets. Okay. So they're out there. You have 3 parts to the chapter R homework on my math lab. Okay. So with that, I'm going to let you go for the Memorial Day weekend. Try to get some work done over the weekend, and I'll be back in the office on Tuesday. But if you have a question over the weekend, though, don't be afraid to email me. Please don't call, though. I have a tendency to leave my cell phone on my dresser top over the weekend. But I will check it from time to time, though. Okay, so have a good weekend, and I'll see you on Tuesday. Goodbye.